And what shear flow is it's actually the shear force per unit length axially on a beam. And what we use this for is for the design of fasteners in what we call built-up members, which are members made of several pieces of things. So like if I've got wood here that's put together with like 4 different pieces, and the beam, continues down this way. Okay. These are joined, with a glue or fastener of some sort. So what we're looking for here is the force, basically as a function of the axial length. Okay. So how we're going to analyze this is very similar to what we did with the shear analysis from previous time. So again, what we're looking at is the force on the surface that's fastened to another piece. So here is my dA right here, and this is dF acting on it, again, over a distance dx. Now, from the shear analysis, again, that dF is dm over I times the integral of y dA prime. Okay, where dA prime is this surface right here that is on the cross-sectional area. Basically, I'm trying to find the shear flow right at this intersection, so I cut it here, and I've got that little surface over there that is essentially my Q that I'm looking for. Okay, so again, that integral is Q. Okay, now what I'm looking for with shear flow again is force per unit length. So basically, if I divide both sides by dx, so I have df dx, dm dx, and then Q over I, where again Q is this integral. Okay, and then remembering that dm dx is my shear force, I can find what we call our shear flow, which again is the force as a function of the longitudinal length, okay, which equals VQ over I. So this is essentially the same equation as our shear stress, except it doesn't have the T in the bottom. And again, what I'm finding here is the force per unit length, so I can figure out what type of fastener to use, how strong of a glue, how close I should put the nails together, things of that nature. So I would look to the example that I've done to see exactly how this equation is applied to solve our problems.